Hello friend, today I am here in my lecture number 4. The course title is Aircraft Stability and Control. Course code is AAE 014, and as you know that I am Dr. Dwivedi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. And I am going to start as earlier. I am referring the books. The first book which I refer in all my classes is Introduction to Aircraft Flight Mechanics, authored by Yagya. And the second book which I am referring is Flight Stability and Automatic Control by Nelson R.C. So these two books I am referring, and I am taking my all notes from these two books. And these books are very nice, and hope you will refer this book, and this will be very useful for you all students. Today is my Unit 1, lecture number 4. In this, I am going to discuss about the longitudinal applied forces and moments. As earlier, I have described about the different axes which are related with this, and the one is longitudinal axis, then lateral axis, and third one is directional axis or the vertical axis. So this unit belongs to the longitudinal motions. So in this, I am going to discuss about the longitudinal applied forces and moments. So longitudinal means the motion in which the nose is going up or down. The nose of the aircraft, when it goes up or down, then we say that the aircraft is in longitudinal motion. This longitudinal motion occur with reference to the lateral axis, the axis which passes from wingtip to wingtip in the y direction. It is called the y direction. And the longitudinal, the axis which is in the direction of x forward. We are assuming x forward, and this another one is lateral axis which is wing to wing, and it is a lateral axis. In this unit or in this class, I am going to cover some of the topic which are under the longitudinal forces and moments. In this, I will explain about the stability axis system and how it is related with the body axis system. Then next topic will be aircraft drag, and then next topic will be aircraft lift, then geometry for calculating lift and pitching moment derivatives. This will give about the aircraft a diagram in which all the parameters will be explained, like aerodynamic center of gravity, the location of center of gravity, location of the wing, location of tail, etc. will be covered in this topic. And last is the calculation of angle of attack of the wing and the angle of attack of the tail. So these topics I am going to cover in this lecture. Hope you all will enjoy this lecture, and it will be useful for you all people. And it gives a basic concept about the longitudinal motion of any aircraft. So the first topic I am going to cover is a longitudinal applied forces and moments. In this, we can see that there are two independent cases. So one is the longitudinal case, in which pitch rotation, the rotation of the nose with respect to the lateral axis, this is called the pitch rotation, and X and Z translation. It means the aircraft can go in X direction, means forward or backward. Like this, it is a x direction, and z means upward or the downwards. So the longitudinal means it can have the pitching motion, like pitch up. If it is like this, pitch up and down, and in the forward or the rear. So if it is the forward and rear, it is in the x direction, and it can also go up and down. These are the two translational and one rotation motion in the longitudinal. And second one is the lateral and directional motion. In this we have two rotations, that is roll and yaw rotation. You know that this roll is happening with the longitudinal axis. So in this, one wing will go up and another wing may go down. So this motion is called the roll motion. Third one is the yaw motion. In this, the movement of the aircraft with reference to the directional axis or the vertical axis. If you take this as a aircraft, so this is the vertical axis. So if the nose is going left or the right, then it is a yaw rotation. So in this case, in lateral and directional motion, you have the two rotations. One is the roll and another is the yaw rotation. And there is one translation, that is the y-axis. So y-axis passes from wing tip to wing tip. So it can go left or right. So if it is going forward, and if you can do left or right, then it is a y-axis translation. So and this longitudinal motion is relatively independent of the lateral and directional motion. Here I want to say that the longitudinal motion is not related with the directional and lateral motion. But this longitudinal and this roll and yaw, these two motions are coupled with each other, or they are interlinked with each other. If you roll the aircraft, the yawing will be there. If you yaw the aircraft, rolling will be there. It is inherent quality of any aircraft. So these two parameters, that is, one is the longitudinal stability and another is a lateral and directional stability. These two different parameters are considered. So here we have to understand that in lateral and the directional motion, both are interlinked. So if we do one motion, another will be inherently, it will happen. So these two, longitudinal is a separate case and the lateral and directional, these are the separate cases. We cannot club this both thing because longitudinal is totally independent. It is not related with lateral and directional stability parameters. So here we have seen that longitudinal forces and movement in stability axis. So in the next slide, I will go for the stability axis. What is the stability axis? So here we have the three equations. One is Fax1s is equal to minus D. Faz1s is equal to minus L. Ma1s is equal to Ma. Where A is indicating the source, that is from where this force is generated. This Fa, where A indicates that it is an aerodynamic force, and this aerodynamic force is equal to minus D. So this indicates that minus means it is backward. If it is plus means it is towards the x direction, x positive, but here it is a minus D, it is a minus x. So it is in the backward direction. So always this drag will act opposite to the nose. Means it will be opposite, or it will be always in the direction of the wind or the opposite to the motion of the aircraft. So this indicates here. Next one is a Faz1s is equal to minus L. So as we all know that lift is always perpendicular to the relative velocity and it is always upward against to the weight. So always, as per the convention, we have assumed that weight, the direction of the weight is positive, so lift will be considered as a negative. And third one is the, so here we have two forces. One is the drag, which is in x direction, and another is the lift, which is in z direction. I have already explained just now that longitudinal motion, which consists of x and z translation. So these forces, that is the lift, is in the z direction, and this minus L shows that it is against to the weight. So here the sign minus is depicted. Same way, the another one is moment, which is in the longitudinal axis, and here also this is MA, so MA1S. Here I am explaining what type of subscripts are used here and why we are writing so much big in subscript format. So for example, here I have given the first one, that is FAX1S. So what is the meaning of all each terminology here? So here indicates, A indicates that it is a aerodynamic force along x direction. X1, x means along the x direction, that is the stability axis, which is a 1 means stability, steady state. So here force which is generated by aerodynamic force, which is in the direction of x, which is steady state, and S stand for stability axis. So we are considering here as a stability axis for the forces. For the moment, I have here depicted in this slide that MA1S. Here if you see, there is no axis. In the previous we have the x1 and z1, but in this moment we don't have the any axis system, that is xyz. It is without xyz because it indicates an aero pitching moment, because M itself is a pitching moment, and always pitching moment will be with respect to the lateral axis. So it is well understood. So it is not required that we have to put any axis system here. That is, one is steady state defined about the y stability axis. So pitching moment will be always about the y stability axis. So in this pattern we have to write the forces and moments. So it is very easy to understand that in which direction and in which level the forces are acting, forces and moments are acting. Now I will go for what is the stability axis, because in the previous, just now I have described about that the forces are like FAX1S. So what is that S? S stands for the stability axis, because all forces especially we take with respect to the stability axis system. So what is that stability axis system? We can see in this diagram. In this diagram it is represented two axis system. One is the body axis system, another is the stability axis system. If you see here, all are converging in one point, that is known as the center of gravity. All the motions with respect to the center of gravity, it is considered. So if you see from here, the XB, which is passing from the center of gravity towards the nose of the aircraft. YB is from the center of gravity towards the starboard side of wing. And third one is the ZB, which is perpendicular towards the earth. So this is the right hand rule. So in this, all the three axes, they are perpendicular to each other. But if we see here in this diagram, if we rotate the nose to alpha in xz plane, it is a vertical plane. If we rotate like this, if this aircraft, it is the nose and this is the tail. If I rotate positive, so this will be XB, but the relative wind will be the XS. S stands for the stability axis. So what is the angle it is turned? It is also called the angle of attack. So how much angle of attack is changed, that the variation of change will also be felt in the vertical component, that is the ZB. ZB will also move towards the one side alpha angle of attack. But if you see the right side, that is the starboard side of the axis, that is the body axis and the stability axis, both will remain same. So in this, it is very nice and it is very easy to explain this thing with respect to the stability axis system. So this system is very popular to finding out the stability and the forces, especially the lift and drag forces, because in longitudinal motion, because in the longitudinal motion we change the angle of attack, that is the alpha. So it is easy to understand. In this, what happened, the relative wind of the aircraft is parallel to the free stream velocity. So it is very easy also to measure the angle of attack and find the stability axis and to find the aerodynamic forces and lift forces like lift and drag very easily. Here also I gave one more diagram. In this we have stability axis system and the body axis system. In this, if you want to convert the stability axis system to the body axis system, we have to give a rotation of alpha, where alpha is the angle of attack. And this alpha is in the xz plane. It means it is in a vertical direction. So in this vertical direction, your alpha is counted or it is considered. So it is to rotate, because why we consider the body axis system and the stability axis system. So it is very easy for the pilot, because pilot is sitting on the aircraft and his motion has to be considered first. He is the first priority and he is sitting on the aircraft, so it is the body axis system. So, and he is also moving the aircraft, doing the maneuvering, in which nose and all the aircraft will move as per his directive. So this stability axis system and body axis systems are with considering the pilot's point of view, because pilot is on board the aircraft and he is the person who is handling the aircraft. For the safety and other issues, pilot's consideration is very much important. So I have discussed about the stability axis system. In this, how to rotate and what are the axis systems to be considered. Now I am going ahead with this only. So in this previous one, for a small angle of attack, body axis forces and stability axis systems are considered in terms of lift and drag would be very small. So we can use this expression for the lift and drag. So what are these expression? It is Fax1b is equal to minus d. It is where d is a drag force and it is in the opposite to the positive x direction. So it is a minus. And next force is Faz1b, which is, in that previous one it was s, Fax1s, but here it is a b. So b is here indicating as a body axis system. As just now I have explained that pilot is in body axis system, not in the stability axis system. So we have to consider the body axis system. For a small angle of attack, the stability axis system and the body axis system are nearly same. It is not exactly same, but both are approximately same. So it is we always consider the body axis system. So it is represented here Fax1b, which is approximated to the minus d, and Faz1b, which is the vertical force, which is also called the lift. This lift is shown as a minus L, as already explained, that it is opposite to the weight. Weight is always considered as a positive direction as per our consideration. Lift can be represented entirely along the Z stability axis and drag can be represented entirely along the X stability axis. So by this representation, we can say that the lift is always in the direction of the Z and the drag is always in the direction of X. The body fixed stability axis is best thought of as a stability axis permanently fixed to the aircraft and a given trim or steady flight condition. Okay, so for this reason, we consider that the body fixed axis system is a best thought, as the stability axis is permanently fixed with the aircraft at given trim and steady state condition. So these are the issues in which we have to consider and we have to give the first priority to the body axis system. Here now, as we know that in the longitudinal axis, we have the two forces. One is the aircraft drag, another is the aircraft lift, and third one is the moment. That is the longitudinal or pitching moment. So I will go one by one. In this, I will be trying to cover two forces, that is the aircraft drag and aircraft lift in this lecture. And the next lecture, I will try to cover the longitudinal or the pitching moment. So what is the drag? So drag is a force which is trying to resist the motion of the aircraft. Okay, and its direction is always opposite to the motion of the aircraft or in the direction of the relative wind. So drag will always try to resist or try to pull down the speed of the aircraft, and aircraft drag is expressed using the drag coefficient, that is called the CD, as drag is equal to CD Q bar S, where CD represents the total aircraft drag coefficient and is a function of angle of attack alpha, and IH is the incidence angle of the horizontal tail, and it is also a delta E. It is a delta E is a deflection of the elevator, so that a similar first order Taylor series may be used to define the total aircraft drag coefficient CD. So here the CD is equal to CD dot star plus CD dot alpha plus CD IH plus CD delta E delta E. Here we have mentioned one star at the CD naught, and this CD naught star is defined as the value of CD when alpha, that is the angle of attack, and the angle of incidence of the horizontal tail and the deflection of the elevator, these all things are 0, then it is considered as a CD naught star. Here we have another term which is the CD alpha. This CD alpha is a derivative which is a change in CD, that is the coefficient of drag, with change in angle of attack alpha. So this is CD alpha, it is a derivative. This indicates that if the variation of angle of attack is happening, the variation of coefficient of drag will also happen. So this is very important parameter to study. In all the derivatives are very important, which gives the status of the aircraft in different conditions. The second derivative is CDIH. This IH, this is change in coefficient of drag with change in stabilizer's incidence angle, that is called IH. Here also, if we change the angle of incidence of the tail plane or the horizontal stabilizer, there is a change in coefficient of drag, and this derivative is giving the how much is required for this different angle setting of tail plane. Third one is the CD delta E, where delta E is a elevator deflection. So this is the change in coefficient of drag with change in elevator angle, that is delta E. So these three parameters, this CD is the directly, or it is a function of these parameters, which are angle of attack. The second one is the incidence angle of the horizontal tail, and third one is the deflection of the elevator. So if you want to calculate this all, the coefficient of drag, the total coefficient of drag. We should know these all 4 parameters, and then we can easily calculate the total coefficient of drag. Now, the drag coefficient is also a function of dynamic pressure. It is also called the Q. The dynamic pressure is half rho V square. To account for aeroelastic effect, if the assumption of rigid body is not valid. Now, normally we assume that body is the rigid, but if we are not assuming that body is rigid, then we have to take the consideration of dynamic pressure and Mach number and the Reynolds number of the aircraft. So as we know that these all 3 parameters are to be considered, and the drag coefficient, that is the CD, is the function of all these 3 also. The previous one 4 plus these 3. First one is the dynamic pressure, second one is the Mach number, and third one is the Reynolds number. I think you all know what is the Mach number and Reynolds number, so I should not explain in detail in this lecture. The next is the expression for the CD requires that CD naught, CD alpha, CD IH and CD delta E are defined at appropriate Mach number and Reynolds numbers conditions, and that aeroelastic effects are negligible. So we are considering that aeroelastic effect is negligible. It also assumes that CD naught star includes appropriate skin friction and pressure drag contribution. So in this CD naught star, it is CD naught plus the other factors which are to be considered. In the previous equation of Taylor series, which I have mentioned before, provides a representation of CD suitable for. It is suitable for stability analysis, because we have to do the stability analysis, because alpha is our perturbed longitudinal motion parameter, and trimmed flight analysis, because IH and delta E are the longitudinal control surfaces used to trim the aircraft. So here this Taylor series is the CD is suitable to do the stability analysis and trimmed flight analysis. We have to understand about the CD naught star. Here we have mentioned here the CD naught star, and what is the difference between CD naught and the CD naught star. It is mentioned here. Here one diagram is also there. So we can see that neglecting the terms like CDIH and CD can be written as CD is equal to CD naught star plus CD alpha alpha. This is equation 1. And if you see our aerodynamic, in the aerodynamics we have studied about the parabolic drag polar, which is also CD, or the total CD is equal to CD naught plus CL square by pi E AR, where AR is a aspect ratio and E is a efficiency of the wing. So we can see that CD naught and the CD naught star are not the same. Both are not the same. The first one, that is the CD naught, is parasite drag, and the latter one, that is the CD naught star, is the drag when alpha, delta E and IH are 0. And CD alpha can be calculated from the equation, that is the CD alpha is equal to 2CL1 CL alpha by pi E AR, where AR is the aspect ratio. So CD naught star can then be defined from the plot as given in the figure. If you see in this diagram, we have the 2 plots. One is for the equation B, that is the polar diagram, which is not a linear. It is a curvature and it is a parabolic. Curvature is there. But another equation, that is the equation 1, that CD is equal to CD naught star plus CD alpha alpha, and this line is assumed to be linearized drag polar. So we have linearized in this, and if you see here, this is the plot of angle of attack versus CD. So in this, we have seen that there is a point at angle alpha 1 where the drag is CD1, and if you see towards the left, you will get a CD naught, and further towards the left, you will get the CD naught star. So there is a difference between CD naught and the CD naught star. If you see here, a point which is tangent from the CD naught star, if from there we draw a line which is a straight line, and if you see that there is a range of linearity is observed, and this range of linearity is calculated. So this CD naught is always greater than the CD naught star. So in the stability problem, CD naught star is also a very important parameters. So it is explained in this what is the difference between the CD naught and the CD naught star. Both are not same, and there is a basic difference in the equations also. This CD naught star is directly related with the alpha, and this CD is related with the aspect ratio and efficiency of the wing and the coefficient of the lift. So to calculate the CD naught star, we should take the equation A, and to calculate the overall CD, which we have to take the equation B as mentioned in this diagram. Next is the lift, aircraft lift. What is the lift? Lift is a force which is trying to pull up the aircraft, or which is trying to make the aircraft airborne. And this force is always perpendicular to the relative velocity, and this is the force which is countering the weight of the aircraft. So every aircraft will consist of sufficient weight, and this weight has to be handled and countered by the aircraft lift. This force is very important, and how to create this force and how to assess this force is very important. So here I am discussing how the main lift is generated and what are the equations for the lift generation. So here the lift L is considered as a L is equal to CL Q bar S. So here this L is equal to lift. CL represents the total aircraft lift coefficient. Here Q bar is a dynamic pressure which is equal to the half rho v square, and S is a surface area. So here L is equal to CL, Q bar and S. But we have to consider or calculate what is the CL and how to calculate for the total aircraft configuration. Till now we are only considering the airfoil or the wing and all, but now in stability and aircraft stability and control, we have to consider the wing, we have to consider the tail, we have to consider other components of the aircraft. So here CL is equal to CL naught plus CL alpha alpha plus CL IH plus CL delta E delta T by using the Taylor series. It is mentioned here. Here the CL naught is defined as the value of CL when angle of attack alpha, the incidence angle of the tail, that is IH, and the deflection of the elevator all are 0. And in this condition, when all these three things are 0, whatever we are getting the lift coefficient, this lift coefficient is known as the CL naught. CL is also the function of the dynamic pressure Q as in the drag, and Mach number and also Reynolds number. So coefficient of lift is also the function of these all three parameters, and to calculate the coefficient of lift we have to consider a definite or a certain number and certain aerodynamic pressure and certain Mach number and a fixed or certain Reynolds number for a particular condition. So we have to calculate this all the parameters before calculating the coefficient of lift. Here just I have mentioned geometry for the calculating of the lift and pitching moment derivatives, that is the CL alpha and CM alpha, and what are the parameters which we have to consider in the aircraft. Here we have considered the fuselage, then wing, and then tail. So if you see this diagram, we have taken as a datum line as a leading edge. Leading edge is the datum line. In this, from this datum line, all the distance which is to be calculated are mentioned. Okay, fixed here a horizontal tail and a wing and the fuselage. So here these three components are considered. If you can see here the XX is the stability axis, and another is which is passing from the nose via the center of gravity, that is the wing chord line. So if you see here here we can see that the free stream velocity V infinity is making angle alpha with XX, that is the main reference line or the fuselage reference line, and it is a alpha. But if you see the wing chord line, it is making IW. Okay, so total, if we consider the total angle of attack of the wing, it is the alpha plus IW. If you see the tail, in tail also we have the incidence angle which is mentioned as the IH. As already I have explained this IH is the angle between the fuselage reference line and the chord of the tail plane or the chord of the horizontal stabilizer. So this is indicated as a IH, and here we have the different distances. One is the XAC WF. WF means wing and fuselage. So it is aerodynamics. AC means aerodynamic center. The distance between leading edge of the wing to the aerodynamic center is known as XACWF. XCG, the distance between aircraft center of gravity and the leading edge of the wing, is known as XCG. And XACH, it is the distance between the leading edge to the aerodynamic center of the tail plane or the horizontal tail stabilizer. So these are the distances which are covered from the datum line, and this datum line is passing through the wing leading edge. So here tail plane or the horizontal stabilizer is producing a lift which is given as a LH, and the lift which is produced combinedly by the fuselage plus the wing is known as the LWF, that is the lift produced by wing and fuselage. And here we have the IW. IW is the angle of the wing with respect to the aircraft center line or the fuselage reference line. Here we have also mentioned MACWF, that is the moment of with respect to the aerodynamic center of wing and fuselage. So this is given here. The note is mentioned that MACW is shown as a positive, but it is usually negative. So this diagram represents all necessary detail of the aircraft to calculate the geometry and to calculate the lift and the pitching moment derivatives, which will be done in the next class. But I am going to take some issues related to this diagram. So here calculation of angle of attack of the wing and tail. First we have to start that what is the actual angle of attack. What is the angle of attack? It is the angle between the relative wind and the x-axis of the aircraft, or it is the angle between the relative wind and the fuselage reference line of the aircraft. Here we take as a angle of attack experienced by the wing. It is alpha W. This alpha W is equal to alpha plus IW, where alpha is the angle of attack between relative wind and the reference line of the aircraft, and IW is the incidence angle of the wing which is installed in the aircraft with reference to the aircraft reference or aircraft fuselage line. So angle of attack at the horizontal tail. So what will be the angle of attack at the horizontal tail? That is the alpha H. I think we know that the tail is behind the wing and there will be lot of downwash. So I have shown here in the diagram that how the angle of the tail plane is varying with respect to the aircraft angle of attack. So if you see here, V infinity in this figure, V infinity is the relative wind or the free stream velocity of the wind, and here V downwash, and here is we are getting VH. So this VH is equal to the vector sum of V infinity plus V downwash. So here we get one more angle that is called the epsilon. This angle between the relative wind and the angle between the wind which is passing from the tail horizontal stabilizer. So this is the angle epsilon. This angle epsilon, which is the downwash angle, is equal to epsilon 0 plus epsilon d epsilon by d alpha into alpha. So it is also related with alpha, means angle of attack. So this epsilon 0 is the downwash angle at 0 aircraft angle of attack and angle of attack at horizontal tail, because we have to consider angle of attack at the horizontal tail. It is our interest. So this alpha H is equal to alpha plus IH plus tau E delta E minus epsilon. So where this tau E is called the elevator effectiveness, it is a ratio that relates a change in angle of attack to a change in deflection of elevator. So it is a ratio, and it is a ratio that relates a change in angle of attack to a change in deflection of elevator. So this is the equation where alpha H is equal to alpha plus IH plus tau E delta E minus epsilon. So this term we have to, what is the geometric description of elevator effectiveness? That is the tau E. So here we can see in this diagram that in the first, with the orientation of the relative wind and the front of the portion of the aircraft is staying fixed, and elevator deflection delta E produces a change in the orientation of the chord line, which in turn changes the angle of attack of the airfoil. The larger the chord of the elevator is relative to the overall chord of the airfoil, the larger tau E will be. We can see here that in this diagram, I have shown here that delta E is equal to 0, means there is no deflection of the elevator, and the angle of attack of this horizontal tail is 5 degree with respect to the free stream velocity V infinity. If we see the next diagram, in which we have deflected elevator by 15 degree. So by deflection of this 15 degree, the location of the chord is changed, because chord defines a line which is passing from the leading edge to the trailing edge of any airfoil. So if we have deflected the elevator down, so the angle of attack is also changed. If you see the first figure in this, the angle of attack alpha 1 is a 5 degree at 0 deflection of elevator, and the second diagram, if you see that elevator is deflected to 15 degree, however we have not changed the angle of horizontal stabilizer. But if you see the diagram, you will see that there is a deflection of from 5 degree to 10 degree in the angle of attack of the tail stabilizer or horizontal stabilizer. So we can calculate that tau E is equal to delta alpha H by delta dE. So here it is 5 degree and now here it is a 15 degree. So 5 degree by 15 degree. So this tau E we will get 1 by 3. So this is playing a very large effect on the aircraft, and this we can also do in our modeling. We are preparing our models, and these models we can do a study on the wind tunnel, that how these things can be varied and how this can really affect our aircraft. So in this way, this thing is completed. I have completed my lecture, and I hope you all have understood this thing. I will say one thing, that whatever I am teaching here, this all things we can carry out with the help of the wind tunnel or the CFD. Just like in this only, the effect of this deflection of this elevator we have seen here, and we can do the aero modeling or prepare one aircraft. In this, the aircraft can be tested inside the wind tunnel, and a small project can be made by the student, and this can be a very unique piece of research, and these small things can be done by each and every student. So try to do these all things, and it is very good. And I'm ending my this lecture here, and next class I will further go for the detailed analysis of the aircraft lift when it is connected with the wing and the fuselage, also when it is the tail or the horizontal stabilizer is fixed. So my next lecture will give about the lift and the moment of the aircraft when considering all component of the aircraft. So thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.